The reactor beside this Pennsylvania river partially melted down in 1979, and its surviving unit ran for another 40 years before closing in 2019 because it could no longer make money. Now that unit is being rebuilt for 2027, and almost everything about its return looks familiar except the customer waiting for its electricity because the customer is not a city or utility, but Microsoft, and similar agreements now connect Meta, Amazon, and Google to nuclear projects across the country. The public explanation is that artificial intelligence needs clean electricity around the clock, and that explanation is true, while the deeper transaction concerns something scarcer than power and begins with infrastructure granted decades before a data center existed. At 4 in the morning on March 28, 1979, a feedwater pump stopped at 3 Mile Island Unit 2, and the turbine disconnected from the generator, while 11 seconds later, the reactor shut itself down and every major automatic protection system initially performed its designed task. Pressure inside the primary cooling system rose, and a relief valve opened as expected, but the valve stuck after the electrical command told it to close, while the control room display confirmed only that a closing signal had been sent, rather than its physical position. Operators therefore saw a closed indication while coolant escaped through an open valve, and the reactor slowly drained through plumbing they believed was isolated. Other instruments showed rising water in the pressurizer, and the crew interpreted that reading as evidence that the system was becoming too full, rather than evidence that steam was displacing coolant elsewhere. Emergency injection automatically pushed replacement water into the reactor, but the crew reduced that flow because training warned against filling the pressurizer completely, and their intervention protected against the imagined condition while worsening the real one. Within about 2 hours, the upper core was uncovered and temperatures climbed until fuel cladding failed and roughly 1/3 of the fuel melted, while chemical reactions generated hydrogen, and officials spent 2 days determining whether the gas could explode beneath the vessel head. Pennsylvania advised pregnant women and preschool children living within 5 miles to leave, while confused announcements carried uncertainty far beyond the plant boundary. But the containment building held, and the releases were small enough that decades of public health studies have detected no resulting health effect. The machinery contained most of the physical accident, but an information failure inside the control room transformed a manageable malfunction into the defining American nuclear disaster because the reactor displayed what its controls intended rather than what its equipment had done. The accident destroyed less machinery than confidence in the financial plans surrounding American nuclear power, because more than 200 reactors had been ordered or were under construction during the industry peak, and most unfinished projects were eventually canceled. Their concrete shells still stand as monuments to money committed before forecasts weakened and costs accelerated, while longer reviews and stricter requirements met early 1980s interest rates that turned every delayed year into another enormous financing charge. A reactor consumes billions before selling its first unit of electricity, and borrowed money accumulates throughout licensing and construction. The technology could still produce power, but the project structure could no longer produce a return that utilities and investors would reliably accept. Several previously ordered reactors eventually entered service, and later projects at Watts Bar and Vogtle survived extraordinary delays, while the ordinary ability to begin a new American reactor and finish it predictably disappeared for roughly 3 decades. The next threat arrived without an evacuation plan, because shale drilling began producing natural gas at enormous scale around 2010. Competitive electricity markets accept generator bids until demand is covered, and the final accepted unit often determines the price paid across the market. Gas turbines became that unit more often because fuel was abundant and their plants could be financed quickly, while a large reactor carried permanent staffing, maintenance, security, and regulatory expenses, even when wholesale prices collapsed. A reactor can't remove those fixed costs or disappear whenever gas prices fall and return when the market improves. So Kewaunee closed in 2013, shortly after relicensing, and Vermont Yankee followed in 2014. Indian Point closed its remaining units in 2020 and 2021 after political pressure, and market conditions converged, while 3 Mile Island Unit 1 closed in September 2019, despite operating safely under a license extending until 2034. These closures did not mean the machines had stopped functioning, because several had recently passed reviews required to continue, and instead showed that dependable electricity could become financially worthless when the market had more supply than it would pay for. California provided an early countersignal when reliability concerns led lawmakers in 2022 to preserve Diablo Canyon after planning its closure, and before artificial intelligence campuses became the public justification for keeping reactors alive. The United States built commercial reactors across roughly 90 sites, and today 94 operating units generate electricity at a smaller number of stations, while other sites contain retired reactors or unfinished structures canceled before their first sustained chain reaction. For 2 decades, many closed locations represented pure liability, because security, maintenance, waste storage, and decommissioning consumed hundreds of millions while producing nothing but around 2022. Some of the country's most expensive scrap acquired a second identity. What looked obsolete to an electricity trader looked unusually complete to a data center developer, and the telephone began ringing. The change began inside a processor. Die approximately the size of a postage stamp, where billions of transistors perform repeated calculations behind every generated word, image, and prediction, while memory stacks surround the processor and a board carries the package through a server sled into a rack. The latest accelerated computing rack can draw more electricity than 30 American homes use at once, while operating continuously through a training run, and hundreds form rows across several halls, whose cooling equipment creates one campus with the continuous electrical appetite of a small city. This is not simply a building containing computers, because computation may be the product, while power delivery through transformers, substations, backup generators, and cooling pumps is the physical business that makes the product possible. The important feature is not only the size of that appetite, but the shape it draws across every hour of the year. A city wakes and sleeps, while a factory runs shifts, and a steel mill can sometimes accept payment for reducing production during a grid emergency. A training cluster performs one connected calculation across thousands of processors and demands nearly the same enormous power level continuously for weeks or months. Interrupting the cluster can corrupt progress and force operators to repeat work whose computing bill may already reach tens of millions of dollars. Solar panels and wind turbines can supply cheap energy, while batteries move several hours from one part of the day to another. But those resources cannot alone guarantee the same output through every calm night and extended weather system. One mature technology was designed during the 1970s to deliver that flat output for a different industrial age, and its lack of flexibility became a market weakness before artificial intelligence converted the same characteristic into a premium product. A pressurized water reactor is essentially a kettle with an unusual heating element and several barriers separating that element from the outside world. Ceramic uranium pellets sit inside sealed metal tubes which form fuel assemblies inside a steel vessel approximately 12 meters tall with walls roughly a quarter meter thick. Water circulates through the vessel under enough pressure to remain liquid above 300 degrees Celsius and carries heat without entering the turbine before thousands of steam generator tubes transfer that heat into a separate second loop where water boils. The steam turns a turbine which rotates the electrical generator, while a third water system removes exhaust heat through a river, lake, ocean, or cooling tower. And only the first loop normally contains radioactive reactor coolant during normal operation. The nuclear island is distinctive because fission supplies its heat and engineered barriers contain the products, while almost everything after the steam generator is a 19th century steam engine rebuilt with modern alloys, controls, and safety systems. Natural uranium is almost entirely the wrong isotope for an ordinary reactor, because only about 7 atoms in every 1,000 are uranium-235. Increasing that fraction is enrichment, and it separates atoms that behave almost identically through one of the hardest industrial processes humans perform. Modern facilities convert uranium into gas and spin it through cascades of centrifuges where tiny differences in mass become useful after thousands of repeated stages, while the United States once performed much of this work domestically and then allowed most commercial capacity to disappear as cheaper foreign supply took the market. In 2023, foreign suppliers provided about 72% of the enrichment services purchased by American reactor operators, and Russia supplied approximately 27%. Industry estimates also placed Russia near 44% of global enrichment capacity. Congress banned Russian uranium imports beginning in 2024, while permitting limited waivers through the end of 2027, and the policy unlocked about $2.7 billion intended to rebuild domestic conversion and enrichment capacity. Existing reactors generally use uranium enriched below 5%, but several advanced designs require concentrations approaching 20%. This high-assay, low-enriched uranium can support smaller cores and longer operating cycles. But the United States lacks commercial capacity at the scale developers expect. The Energy Department projects demand above 40 tons by 2030, with additional quantities required afterward, while established foreign capability at the relevant enrichment level has largely been associated with Russia and China, and American Centrifuge has begun limited production at Piketon, Ohio. Its demonstration cascade delivered the first material in 2023 and can produce about 900 kilograms annually, which proves the process without approaching projected demand while operating in Pike County, where promoters also announced a data center campus with a $500 billion headline value. A reactor exists to move heat away from a core, while a data center exists partly to move heat away from a chip, and both facilities are cooling systems wrapped around equipment that cannot survive when thermal energy stops moving. Air cooling reached a practical limit as accelerator power density increased and liquid began touching a cold plate mounted directly above the processor. Coolant flows through a manifold and distribution unit before larger pumps and rooftop coolers reject the heat outside. Almost every additional unit of computing electricity becomes another unit of heat somewhere in the building. So cooling determines rack density, pipe layout, water treatment, backup capacity, and the maximum work a site can sell. Large campuses consequently seek the same physical ingredients as major generating stations because they need flat land with controlled access and heavy transmission equipment and enough water or alternative capacity to reject a city-sized stream of heat. A nuclear site already possesses those ingredients because engineers solved the same siting problem half a century earlier. The public story says technology companies are buying nuclear power because it is clean and constant. But the less visible purchase is an electrical address the grid has already accepted, while American interconnection queues recently approached 2,600 gigawatts of proposed generation and storage before withdrawals and reforms reduced the active total. Projects completed in 2025 had spent a median period exceeding 5 years between requesting a connection and reaching commercial operation. And although those figures describe generation rather than identical data center requests, both encounter limited substations, transmission corridors, studies, and engineering staff. Google publicly described one utility quoting 12 years merely to complete the study needed for a new data center connection. Texas showed the scale more directly when its large load queue reached roughly 410 gigawatts in spring 2026, which was about 5 times the generating capacity available across the entire system. Many speculative requests will never be built, but an operating nuclear station has something each proposal lacks. It already possesses switchyards, transmission rights, and an interconnection agreement written decades ago for 1,000 megawatts or more. A developer may still need upgrades and permission, but its electrical doorway already exists, while a model under development today may be obsolete in 18 months. So technology companies cannot plan around a connection arriving after 12 years and are buying more than electricity. They are buying a place in a queue that no longer exists. For most of the shale era, the obvious alternative was a combined cycle gas plant, which could be built faster than nuclear and operated whenever the market needed it. But that answer weakened when manufacturing capacity became another queue, and only 3 global suppliers produced the largest advanced turbines at meaningful scale. General Electric Vernova reported roughly 100 gigawatts of backlog and slot reservations during 2026, while available delivery positions extended toward 2030. And industry estimates placed combined cycle lead times around 5 to 7 years, with some schedules approaching 8. Wood Mackenzie projects large turbine prices near $600 per kilowatt by the end of 2027, which would be almost 3 times the 2019 level. A gas plant also needs a pipeline connection, and air permits, and water and a grid interconnection that may be no faster than the campus it serves. Some developers therefore turned toward banks of enormous reciprocating engines derived from marine and industrial machinery, because smaller units could arrive sooner. And although the design sacrifices efficiency and space, its schedule value can overwhelm those disadvantages when computing equipment waits without power. The largest corporations on Earth are simultaneously contracting for ship-scale piston engines and reactors built 40 or 50 years ago. They are doing this because the ordinary path through turbines, transmission, and permitting no longer fits the computing calendar. Microsoft agreed to buy the entire output of 3 Mile Island Unit 1 for 20 years and supported its renaming as the Crane Clean Energy Center. The reactor is rated at 835 megawatts, and its target return moved from 2028 to 2027. Constellation began rebuilding equipment and training operators, while federal financing supplied a $1 billion loan. But fresh fuel and regulatory approvals still stand between that work and commercial generation. Meta signed another 20-year agreement for the 1,121 megawatt Clinton reactor in Illinois, beginning in June 2027. And although that contract creates no reactor, it gives a working plant revenue certainty against a closure its owner said was otherwise likely. Amazon bought a campus beside Susquehanna and later entered a front-of-meter agreement covering as much as 1,920 megawatts. The restructured contract reportedly carries a value near $18 billion across 17 years. Palisades in Michigan became the first retired American reactor to receive federal approval, reversing its decommissioning status toward operation, while Google attached demand to planned small reactors. Across announced hyperscaler agreements and development plans, the claimed capacity approaches 10 gigawatts, although some preserves existing output and some remains attached to unbuilt machines. Corporate presentations describe these transactions as capacity, but the facilities occupy towns where one plant shapes an economy. Middletown, Pennsylvania endured the worst accident in American commercial nuclear history and then watched the undamaged unit employ neighbors for another 40 years. When that unit closed in 2019, skilled workers left and local suppliers lost a customer that had purchased maintenance, security, transport, and services each year. While its return restores jobs and tax payments, even if every unit of contracted electricity is financially assigned to a distant company. Covert Township, Michigan lost Palisades in 2022, along with several hundred positions and a major part of the surrounding tax base. Local governments built budgets around the plant and then faced fewer resources for schools, roads, emergency services, and public facilities. Clinton, Illinois received repeated warnings that its reactor could close before learning that a 20-year agreement with a social media company might keep it operating. The corporate buyer became inseparable from local arguments about payroll, municipal revenue, and whether younger workers could remain nearby. Support is often loudest in the nearest community, while opposition may organize farther away because nearby residents experience both the risk and the wages. Nobody in Middletown voted on whether Microsoft should claim the output across the river, and the practical choice concerned whether jobs and taxes should return. Those questions differ in theory, but collapse toward the same answer when one industrial site provides the most stable employment for many miles. The electricity contract, therefore, rearranges local politics before the reactor produces anything. Amazon originally pursued an arrangement allowing the Susquehanna campus to take much more power directly behind the meter. Electricity would cross a short private connection instead of traveling through the public network and returning as an ordinary retail purchase. Federal regulators rejected the associated agreement in November 2024 by 2 votes to 1 because the filing had not justified changes that could shift transmission and reliability costs toward remaining customers. A reactor serving the grid contributes energy and capacity that planners count when arranging reserves and transmission. Moving 1,000 megawatts behind a private boundary can therefore change who pays for services previously shared across millions of users. Amazon and Talon later restructured the transaction through the grid under a front-of-meter agreement reportedly worth about $18 billion across 17 years. Regulators also directed the regional operator to develop rules because similar collocated loads would keep appearing. Federal action in 2026 accelerated that framework while requiring large users to bear their complete connection upgrade costs. The unresolved issue is whether assigning an existing reactor to a data center adds electricity to the country or reallocates electricity that served other customers, because the contract can provide one answer while the physical system provides another. Data centers represented about 4% of American peak summer electricity demand in 2025, according to Goldman Sachs estimates. The same analysis forecasts growth from roughly 31 gigawatts in 2025 to 66 gigawatts in 2027 and an 8.5% peak share. Those are projections rather than metered facts, and they depend on campuses being completed and filled as announced. They still enter utility plans because transmission and generation must be ordered years before the load appears. The regional grid, called PJM, serves about 67 million people across 13 states and the District of Columbia, while its capacity auction pays generators to remain available in future years and reached the approved price ceiling for 3 consecutive auctions by July 2026. That result does not flow only from data centers, because retirements, fuel costs, transmission limits, and market design also affect price. National residential electricity prices have risen roughly 36% since 2020 by federal comparisons. During the first half of 2026, utilities asked regulators to approve $18.6 billion in combined electric and gas rate increases, according to the Powerlines tracker. A request is not an approved bill, and the total includes old transmission, storms, gas volatility, and investments unrelated to computing. The demand curve nevertheless bent upward when the largest new industrial loads in a generation arrived. Regulators must decide who funds construction for those requests and who carries the cost when a forecast proves wrong. Major industrial customers also negotiate confidential rates and special contracts, so the public cannot always see whether a campus pays its complete share of transmission, reserves, and local infrastructure. People living beneath those lines did not negotiate the nuclear agreements and encounter their outcome through monthly bills. Small modular reactors are intended to replace cathedral-sized projects with standardized units assembled repeatedly in factories. A smaller unit needs less capital for each decision, and factory production could move complex work into controlled conditions with a permanent workforce. The proposition is reasonable because repetition improved cost, quality, and delivery in industries from shipbuilding to commercial aircraft. The promised learning curve has not yet appeared in Western commercial operation because no Western small modular reactor was selling electricity from a completed fleet in early 2026. The flagship American project paired NuScale modules with municipal utilities in Utah and planned construction in Idaho. Customers withdrew and the project ended in 2023 after its estimated cost rose from roughly $5 billion in earlier configurations to more than $8 billion in the final federal estimate. The cancellation did not prove a failed reactor because construction never began and the design passed important reviews. But it proved a failed contract after utilities decided the escalating price and schedule no longer protected customers. Published first unit estimates vary widely and often land between roughly $80 and $150 per megawatt hour. The cheap promised number arrives only after factories, suppliers, regulators, and crews repeat one design many times, and someone must finance the expensive units before that learning exists. Technology companies now appear beside nearly every serious Western project because they can sign long contracts and tolerate risks that utilities struggle to pass through to households. The companies needing the electricity are underwriting the machine intended to manufacture it, while the United States debates restarting machines from the 1970s. China continues building reactors at a pace no other country attempts. Industry analysts expected around 15 units to enter service worldwide during 2026 and add close to 12 gigawatts if schedules held. The difference is not hidden physics, because engineers in both countries understand reactors and international suppliers can fabricate major components. The decisive difference is the institution carrying construction risk and the price it pays to borrow money. China treats nuclear construction as strategic infrastructure financed through state-directed institutions with repeat orders and predictable capital, while the United States usually treats each plant as a private project that must clear a return threshold inside a competitive electricity market. That structure magnifies delays because interest accumulates while unfinished machinery earns nothing, and canceled projects scatter suppliers and crews. American nuclear history since 1979 is therefore partly a financing story presented as a technology debate. 4 technology companies changed the equation quickly because their balance sheets can promise revenue for decades, and their computing schedules value time differently from an electricity market. Restarting a reactor bears little resemblance to flipping a breaker because an owner must reverse legal declarations that made shutdown permanent. The operating license and safety analyses must be restored, while inspectors confirm that inactivity did not degrade pumps, valves, cables, structures, or procedures. Fuel must be fabricated and delivered for a machine whose previous inventory may already sit in dry storage. A control room must also be staffed around the clock by individually licensed people, and the emergency organization must be rebuilt around them. Palisades targeted October 2025 and then moved its expected restart into 2026, while Crane was announced for 2028 and later pulled forward to 2027, which is unusual enough to deserve scrutiny. No retired reactor has yet delivered a commercial megawatt specifically under these hyperscaler restart agreements. Money is committed and equipment is moving, but every completion date remains a promise until the generator synchronizes with the grid. One input cannot be accelerated with a larger purchase order because federal regulators license every individual who operates a commercial reactor. Candidates complete extensive classroom, simulator, and plant training before written examinations and operating tests determine whether each person may control the unit. An initial program commonly takes 18 months to 2 years, and examination failure is a real possibility rather than a ceremonial hurdle while Crane has been assembling a new organization with roughly 90 people reported across its initial training pipeline. When 3 Mile Island Unit 1 closed in 2019, its experienced workforce did not remain indefinitely beside an idle control room. Employees retired or moved to other plants while their plant-specific knowledge dispersed. A supplier can deliver a pump, and a contractor can replace cable, but neither can sell an instantly licensed operating crew. Every restart depends on recruiting humans early enough for a regulatory clock that cannot simply match the corporate schedule. This constraint attracts less attention than turbines, fuel, and transmission. Yet it may decide which promised restart reaches the grid first. The confirmed column contains contracts and regulatory actions rather than finished electricity. Microsoft has a funded 20-year agreement at Crane, and Meta has signed its 20-year Clinton purchase, while Amazon owns the Susquehanna campus and buys through the grid. Federal regulators rejected the first behind-the-meter proposal and later required broader rules for large co-located customers. Palisades received the first approvals, reversing a retired reactor from decommissioning status toward operation. But that milestone does not mean commercial generation has resumed. The unsettled column includes schedules and advanced reactor costs, and whether projected data center demand appears. It also includes whether these arrangements add new national supply or reserve old output for a new owner. A restart is not new capacity, because it returns old capacity and can contract the output before its first new megawatt reaches the system, which matters whenever preservation is described as expansion in a company announcement. The contracts extend for 20 years, while the demand curve supporting them is scarcely 2 years old. Computing requirements may keep rising, but training could become more efficient, or financial returns from larger models could flatten before the agreements expire. A technology company might then hold decades of payment obligations for electricity it no longer needs at the expected scale. The reactor would still produce a valuable commodity that another customer could use, so the grid would not inherit a useless machine. The argument behind the transaction would suffer because the immediate restart case depended on one industry's urgent need for continuous power. Climate value and energy security may follow, but neither explains the speed or the identity of the original buyer. If computing demand softens, then reactors and contracts can remain while the cost stays with whoever accepted it. Long certainty protects construction from one risk by transferring demand risk into the future. For 50 years, the American argument over nuclear power concerned meltdowns, waste, and what happens to a town when complex machinery fails. That argument never reached a common answer because investment collapsed and cheap gas made the unresolved dispute less urgent. That argument never ended. It was interrupted when a new industry required a specific shape of electricity and discovered that the necessary land, water, transmission, and permits were already assembled behind retired plant gates. The reactors are returning because the country found an urgent customer before it found agreement. The surviving reactor at 3 Mile Island is scheduled to run again for a machine that did not exist when the plant closed. Its power will cross infrastructure approved decades before artificial intelligence entered the contract. Whether this represents progress depends on the ownership question beneath every financial announcement and engineering milestone. Who is this power actually for?